And he's also been recently working in various areas of optimization. Starting this past fall, he moved to Johns Hopkins, where he's currently an assistant professor in the Department of Electrical and Computer Engineering, and also a professor in mines. We're really delighted to have him, and we look forward to his talk.
Thank you, René, for the kind introduction. Hello, everyone. So it's my great pleasure to speak in this fantastic event. So today I'm going to talk about some of the control theoretic and optimization-based tools that I have been recently developing for the analysis and synthesis of neural network-driven systems with performance guarantees. So over the past decade, we have seen a surge of interest in using learning, or more specifically, deep learning in a lot of domains, and control is not an exception. So here you can see a typical control pipeline. So the goal in control engineering, broadly speaking, is to connect data to actions. So we have sensors, we have perception, planning, and control. So there are a variety of well-justified reasons to use learning in various parts of this pipeline. For instance, in perception module, in order to basically localize an autonomous system in a dynamic environment, we might want to use deep learning to do object detection, or for instance, when we have a low-level feedback controller, so we typically need a model. And if we don't have a perfect knowledge of the model, or we don't have any model at all, we may want to use direct interaction with the environment in order to implement control action. And we can see that actually learning and deep learning have been very successful in control. They have achieved superior performance in a lot of complex control tasks that the problem formulation for control is even unclear how we can formulate a model for the system. However, this is almost relatively well known that basically neural networks can be very fragile to input perturbations, meaning that even a slight perturbation to the input of the neural network can drastically change the output of the neural network. And this is, of course, a basic, a fundamental limitation in the adoption of deep learning in safety critical systems. So in order to really adopt deep learning technology and take advantage of all the performance that we get out of these technologies, we require basically strict guarantees of stability and safety for learning-enabled dynamical systems. So we require deterministic as opposed to probabilistic guarantees so that we can ensure that these systems will be safe in safety critical systems, especially when humans are involved. So motivated by these big limitations, I have been trying to, in collaboration with my colleagues, I have been trying to develop some of the tools in order to move towards this direction of providing guarantees for neural network driven systems, both after training and during training. So here's a rough outline of the talk for today. So the talk is 3 parts. In the first part, I'm going to talk about verification of neural network driven systems using a convex optimization framework. In the second part of the talk, I'm going to talk about learning stability certificates for neural network driven systems. And the third part, I'm going to talk about how actually we can enforce some of these guarantees within neural network policies during training, and we still have those guarantees after training. So I'm going to first start with the first part, verification of neural network driven systems via convex optimization in collaboration with my colleagues at University of Pennsylvania. So the problem of neural network verification is very simple. So given a neural network F and a bounded set of inputs to the neural network, our goal is to compute the output set of the neural network. Of course, this problem is computationally intractable because of the high dimensions in the input space of the neural network, as well as the presence of nonlinearities in the neural network. So we would like to at least be able to localize or over approximate the output reachable set. Basically, this problem is also relevant in robust training. So it's not just a post-training procedure after training we would like to verify the neural network, but also during training, we might want to solve problems of this form. For example, in robust training, a possible formulation of robust training is to, instead of minimizing the regular loss function in deep learning, we basically minimize a worst case value of the loss function over basically additive norm-bounded perturbations to the training data points. So basically, we have, from an optimization perspective, we have a min-max optimization problem where the maximization problem, in order to be able to solve this maximization problem, we need to solve reachability problems of this form that I just described. However, since robust training is not completely related to what I'm going to talk about, so I just stop here and don't talk about it now. So let's think about verification through the lens of optimization. So it's typically the case that we can rephrase verification as a constraint satisfaction problem from an optimization perspective. So given a constraint function J and an input set, bounded set X, we would like to verify whether J of f of X is less than or equal to 0. So that's the verification problem. So this problem can, of course, be equivalently written as a non-convex optimization problem, where basically we first maximize the constraint violation, denoted by J star, and then verify whether J star is less than or equal to 0. So here in this figure, you see the two scenarios that can happen. If J star is less than 0, this means that the output set of the neural network won't intersect the 0 level set of this constraint function, as opposed to J star greater than 0, which means that actually the output set will cross the 0 level set. So basically, we can also think of this function J as a function that defines the boundaries of a safety set that we would like to verify, right? So basically, so in order to do verification, we can see that we need to solve this non-convex optimization problem, of course, using like iterative algorithms such as projected gradient descent or ascent. To solve this problem is not very promising because these algorithms are not guaranteed to find a global solution. So basically, we need to we need to find a global solution to a non-convex optimization problem, or at least find guaranteed upper bounds on the solution to this problem so that we can verify this constraint satisfaction. So in order to do this, let me describe how we can find a global solution to this, or at least bound it. So first, let us consider the neural network model that was also discussed in Maxim's talk. So we consider a classical feed-forward neural network with L layers, where each layer consists of an affine operation followed by an activation layer. And then basically we can rewrite this optimization problem equivalently as the following form, where we explicitly incorporate the equations of the neural network inside as constraint inside the optimization problem, right? So if we take a look at this optimization problem, we can see that so if, for instance, J is a linear or concave function, then this constraint is linear. And if the set X is convex, so the troublesome constraint here is this equality constraints imposed by the activation layers, right? So if we can find a tractable representation of this constraint, then we can basically solve this optimization problem, or at least find bounds on it. So in order to do that, the first step is basically try to basically relax this or have a different representation. So first, what we do is that we can basically rewrite this constraint as follows. So basically, we can say this pair belongs to the graph of the activation function. So this is a graph representation of a constraint. And then basically, we ask this question that whether we can find a tractable representation of a graph of a nonlinear function. So in order to do that, I will just focus on a single ReLU activation function, and then basically we can build up the whole representation for a neural network. So suppose that we have the ReLU function, y equal to max of 0 and x over some bounded interval. So if you think of this as a function, it is convex, but we are trying to basically, we should think of this as a graph, as a set in 2 dimensions, which is clearly a non-convex set. So there are various ways to represent this this piecewise linear basically set. So the first representation is a mixed integer representation, basically by introducing an integer variable t, 0 and 1, and writing down 4 affine inequalities. Basically, we can precisely describe this ReLU function. So if we basically substitute these equations into the optimization problem in the previous slide, we obtain a mixed integer programming, linear programming representation of the problem. So there is no relaxation and we can solve the problem globally. However, it's known that MILPs or mixed integer programs are not scalable. They use branch and bounds and they have worst case exponential complexity. So it is not, it's not promising to use this formulation to verify neural networks, especially larger scale ones. So we need to find different representations and then eventually relaxation. So another way of representing this set is by using quadratic plus affine representation, whereby we can exactly represent the ReLU function with combination of 2 affine constraints and 2 quadratic constraints. And then if we substitute this in the optimization problem in the previous slide, then we obtain a non-convex quadratically constrained quadratic program. So from optimization theory, we know that there is a route to do semi-definite relaxation of this problem, which I will discuss briefly in the next slide, right? And then eventually we can go ahead and do a linear relaxation of this, whereby instead of working basically with this non-convex set, we make a convex Hall over approximation of this set, which can be described by linear constraints, and then we obtain basically a linear programming relaxation, right? So, so basically, I'm going to focus on semi-definite relaxations of this problem, and then I'm going to introduce a different perspective on how to obtain a better semi-definite relaxation for this problem. So let me first describe this part. So this is a generic non-convex QCQP. So we are minimizing quadratic functions subject to quadratic constraints. Nothing is convex. So basically here you can see an illustration of the feasible set. So we take the union of ellipsoids and then we take the complement of that, and that's the feasible set. So one way to do convex relaxation of this problem is the so-called lifting, where we introduce a matrix X, which is rank 1 and is supposed to be equal to XX transpose. X is the vector of decision variables. So after doing this lifting, so we end up having a problem that all the objective functions and all the constraints are convex except for the rank 1 constraint. And then the relaxation happens when we actually basically relax this equality constraint to an inequality constraints, and then go ahead and do a short complement relaxation of this in order to find a semi-definite relaxation. And then using this semi-definite relaxation, we are guaranteed to have a lower bound on the objective value of a minimization problem, or equivalently an approvable upper bound on the maximization problem that I just described in the previous slide. The issue with this relaxation is that we are lifting the problem to a much higher dimensional space. So we are going from n decision variables to n plus n squared decision variables. And in our context, n is the total number of neurons in the neural network plus the input dimension. So this is really the main bottleneck, and there is no basically way to control the relaxation, and we don't have any intuition inside what is happening when we do short complement relaxation. And we would like to have a better relaxation with controllable relaxation, which has better scalability. So that's what I'm going to talk about. I'm going to argue that actually we can, by thinking about neural networks through the lens of dynamical systems, we can basically obtain novel results. For instance, So let's take the neural network architecture that I just described. Basically, we can think of that neural network as a linear time-varying system, where the time-varying linear system part are composed of the affine operations in the neural network, and the nonlinearity, which we assume it is the same for all the layers, is the nonlinear function phi, right? And for this dynamical system, each time index corresponds to one layer of the neural network, right? So why is this useful? Why I'm arguing that this is useful is because this is an instance of the Lorey problem, which Maxime mentioned, with the distinction that the linear part is time varying. But if we make the linear part time invariant, which corresponds to recurrent architectures, then we can use a cornucopia of methods from robust control in order to say something about this dynamical system. We have contraction-based results, we have integral quadratic constraints, we have circle Popov criterion, a lot of tools in order to analyze the stability, robustness, reachability of this dynamical system. So basically, that's the route that we are going to take now. So basically, the high-level idea is that instead of working with this nonlinear system directly, we are gonna abstract away this nonlinearity and describe it by quadratic constraints that it imposes on its inputs and outputs. And then we are left with a linear time-varying system subject to quadratic constraints. And people with robust control background already know that we can analyze linear systems subject to quadratics. So everything is either linear or quadratic. So it's quite plausible to think of a semi-definite programming framework to analyze this neural network. So there are various ways to basically define these quadratic constraints, and depending on how we define them, we obtain different results. For instance, we can do reachability analysis on the neural network if we write quadratic constraints in a certain way. If we use a different characterization of quadratic constraints, such as incremental quadratic constraints, for example, we are able to say something about the operator norm of this dynamical system, which corresponds to the Lipschitz constant of the original neural network. So let me briefly discuss these quadratic constraints for just a single activation function and how it is done. So the basic idea, as I said, is to basically describe any nonlinearity that we see in the neural network using quadratic constraints of this form. And a simple example is the class of sector-bounded nonlinearities. So if our nonlinearity is known to belong to this sector, which is formed by these two lines with the slope alpha and beta, then basically we know that we can write this quadratic constraint that describes the input-output relationship of this nonlinearity. However, this quadratic constraint is not restricted to this nonlinearity. Basically, all nonlinearities in this sector satisfy this QC. So what quadratic constraints are basically geometrically, what they're doing is that they're over approximating the graph of the nonlinearity that we are trying to describe by a set of quadratic constraints. So a more tangible example, for example, if we take the ReLU function that we had at the beginning, so basically we can precisely describe this ReLU by intersecting three quadratic constraints. So basically, if we intersect this boundary of this sector plus these two sectors that I have written here, so the equations of the sectors are here. So if we intersect them, we can recover the ReLU function. So where the approximation comes from? The approximation comes from where we basically combine this quadratic constraint. So we make a linear combination of this quadratic constraint to find a single QC where it is parameterized by some multipliers, lambda1, lambda2, and nu, and these will be decision variables in our final semi-definite program. So what we do is that we basically find a parameterized over approximation of the graph of the activation function, and then the STP will decide what over approximation works for the problem that we are trying to analyze. So basically, after doing that, after finding over parameterized family of over approximations of the graph of activation functions, basically we can repeat this and do this for all the activation functions, all the nonlinearities in the neural network. I skip the details, but at the end of the day, we end up having a bunch of parameterized quadratic constraints, and then the way to connect them in order to basically derive a new result is basically use the S procedure from robust control. So if you use the S procedure, which is a very well known and heavily used method, simple method in robust control and robust optimization, basically we use the S procedure to combine all these individual QCs together and verify an end-to-end quadratic constraint for the whole neural network. And this result is in the form of a linear matrix inequality. So I have written the result in a very high level. So we obtain the following result, that we find a matrix inequality, which is linear in our decision variables lambda and nu, and a symmetric matrix S. And we claim that if this linear matrix inequality, if it is feasible, then the neural network is guaranteed to satisfy the quadratic constraint of this form, which is basically parameterized by matrix S, right? So we have basically the end result is that we have a convex condition in order to make a conclusion about constraint satisfaction, and this constraint satisfaction is in this form. And an observation about this result is that compared to the lifting relaxation that I described in previous slides, here the number of decision variables scales linearly with the number of neurons in the network. So basically, we are adding meaningful quadratic constraints, and we are basically we avoid the explosion in the number of decision variables using this approach. And moreover, we can basically move beyond verification and solve other problems as well. For instance, by basically choosing this matrix S, we are going to we are able to basically verify different forms of constraints. For instance, if we would like to do reachability analysis and find the reachable sets of neural networks using polytopes or ellipsoids, basically we can parameterize S, find the convex parameterization of S, and optimize over those parameters subject to this LMI in order to do reachability analysis. So, for example, here is a very simple example to illustrate the effect of this approach compared to the lifting approach. So here we are having a neural network with 2 inputs and 2 outputs, so that we can visualize and compare. And from left to right, we are increasing the depth from 1 to 2 and 3. And the blue point cloud is basically the actual reachable set of the neural network. And the red polytope is the polytope obtained by the method that I just described. We call it deep STP. And the black polytope is basically the polytope obtained by lifting. And we can see a substantial decrease in conservatism and accuracy of deep STP compared to SDR. And the big picture, the big message here is that we are able to add meaningful and not redundant constraints so that we can control the number of decision variables in the semi-definite relaxation. So another advantage of basically this dynamical system perspective is that it's a modular approach. For example, now if we have, instead of just a neural network in isolation, if we have a neural network in interconnection with an uncertain dynamical system, as we typically encounter in robust control, basically, as long as we can basically also model uncertainties or bound them using quadratic constraints, then basically we can integrate these components, modeling uncertainties and the non-dynamical system, into the framework and basically reason about the whole closed loop system, either reachability, either stability, either contraction, using semi-definite programming. So the details are very involved, so I would like to just keep it at high level for now. So for example, we also have an example here where we do reachability analysis of a closed loop system where the system is linear and the neural network basically has learned to mimic a control policy, an MPC control policy. And here we are seeing basically we are able to basically find much better over approximations of the reachable sets as opposed to the lifting semi-definite relaxations. So, so before I finish this part, so far we have, for example, talked about certifying quadratic constraints of this form. By changing the nature of the quadratic constraints, we can derive new certificates. For example, certifying incremental quadratic constraints, which Maxim also discussed in his talk about incremental stability of dynamical systems. So basically, we are also able to certify incremental quadratic constraints of this form on the map of the neural network with respect to two inputs rather than one input itself. And this is useful, for example, in Lyapunov or contraction-based stability analysis of neural network-driven systems, or even for neural networks in isolation. Basically, this incremental quadratic constraint is, you can think of it as a generalization of Lipschitz continuity in L2 norm. So for instance, if we use the matrix S, parameterize it in this way, where LF is a scalar, then the satisfaction of this constraint means that the neural network is Lipschitz continuous in L2 norm with a Lipschitz constant LF, right? So I skip the details, but if we do the abstraction of at the neural level and then we do the S procedure, we end up having, for example, results of this form. So which I have summarized it for the case of estimating the Lipschitz constant. So suppose that we have a one-layer neural network, then we have a linear matrix inequality of this form parameterized by rho and vector lambda. So, and the claim is that if this linear matrix inequality is feasible, then a square root of rho is a guaranteed upper bound on the Lipschitz constant of the neural network. And these parameter alpha and beta are slope parameters of the activation functions, which also Maxim mentioned to it. So there's a close connection here. And before I go for the questions, and I can say that basically having this LMI constraint, then we can find the best upper bound on the Lipschitz constant by just simply minimizing rho subject to this LMI constraint. So I pause here to see if there are any questions before moving to the second part.
Yeah, I was going to ask you, as to you briefly touch on it, which is what is the dependency on the nonlinearity phi, and how is it captured, and say what it would be for a ReLU versus some other nonlinearity that maybe has higher derivatives?
Are you referring to the Lipschitz part specifically or in general?
No, for this theorem in particular, it seems that it's just that the matrix M doesn't depend explicitly on phi, or maybe the dependency is hidden.
Yes. So basically, the dependency is through the constants alpha and beta. So basically, if your activation function is differentiable and the derivative is bounded between alpha and beta, so beta means that it is Lipschitz, it's constant beta, and alpha means that it is a strongly monotone with constant alpha, then we have this result. But we don't need differentiability here. So basically, we can have a non-differentiable version of this as well.
Okay.
And for the case of the ReLU function, alpha is 0, beta is 1. Actually, that's a very good question. So I can also add this comment is that this framework so far doesn't capture the difference between tangent hyperbolic and, for instance, ReLU, because both of them have the same alpha and beta. So it would be interesting. Actually, we have been able to partially address that for estimating the local Lipschitz constant, but for global, it seems that this framework is agnostic to tangent hyperbolic or ReLU. So it would be interesting to actually see how we can distinguish between these two cases when we want to compute the Lipschitz constant.
Right.
So in the second part of the talk, I'm going to talk about basically learning stability certificates in the form of Lyapunov functions for neural network-driven dynamical systems. And again, this is a joint work with my colleagues and collaborators from University of Pennsylvania. So stability analysis of dynamical systems is a long-standing problem in control. So the problem is that we have an autonomous system, x plus equal to f of x, assuming that 0 is the equilibrium point. And the long-standing problem is to how we can certify that this equilibrium is locally stable, and then in addition find its region of attraction. So certifying local stability is not a very difficult problem, because we can do this by local linearization and checking the eigenvalues of the linearized function, the Jacobian of f at the equilibrium. However, finding the region of attraction is a much more complicated problem. So the region of attraction is the set of initial conditions around the equilibrium point for which the trajectories converge to the equilibrium point. So finding this region of attraction is of interest in safety verification, because it captures the transient behavior of the dynamical system and how the trajectories evolve before converging to an equilibrium point. So a very common approach to solve this problem is to use Lyapunov functions. So Lyapunov functions basically are positive definite functions, which are like energy-like functions, which are 0 at 0, positive everywhere, and basically they are they're guaranteed to decrease along the trajectories of the dynamical system, this condition here. So basically the problem is to find a Lyapunov function for an autonomous system, right? And but this is a very general problem, so we can of course not solve this. We cannot solve this problem for general f. We need to be more specific. So this is generally an intractable problem, because this is an infinite dimensional problem in function space. So now I'm going to basically describe a learning-based approach, how to learn these Lyapunov functions, even though I'm assuming that we have a perfect knowledge of the system, but the system is so complicated that we are going to use learning in order to find a Lyapunov function. So it's typical to consider, instead of searching in function spaces, we consider a parameterized family of Lyapunov functions, typically quadratic. So we consider Lyapunov functions of this form, x transpose px, p is a positive definite matrix, and we define the target set as the set of matrices P that renders a valid Lyapunov function. So the first constraint is a positive semi-definiteness constraint, and second constraint is Lyapunov decrease condition, and this condition is basically a linear constraint on the matrix P, right? So this set is basically a convex set. So what is difficult about this? So the goal is to find a matrix P inside this set. However, this is an instance of a semi-infinite convex optimization, because we need to have this constraint for all states in a bounded set. So we have basically a robust constraint. So we need to have this constraint to hold for an infinite number of x's inside a bounded set, right? So I have an illustration of this. So the set is convex, but it is characterized by infinite number of affine constraints. So how to go about this problem? So one can think of basically do some sort of sampling. So instead of trying to satisfy the Lyapunov decrease condition for all the states, we basically relax that and sample from our domain. Let's call it the sample set S, right? So what we are doing geometrically is that we are sampling the constraint, and we are basically over approximating the target set. So we are obtaining an over approximation of the set F, which we call it F tilde. So for example, one possible way is to basically sample, use a distribution over the state space to sample states and basically solve a finite dimensional convex optimization problem and find explicit bounds on the probability of failure. So this is the field of basically data-driven robust optimization or scenario optimization or random convex programs. But the guarantees will be probabilistic. So we will, at the end of the day, we will have guarantees that are not deterministic. So we would like to avoid that as much as possible. So here's the framework that we are going to basically to propose in order to find deterministic guarantees on the Lyapunov function. So our method is composed of two agents or two entities, a learner and a verifier. So the job of the learner is basically, so first we start with a sample set in the state space. So the job of the learner is to propose a Lyapunov function that satisfies the Lyapunov conditions only over the sample set. So this is definitely not going to be a valid Lyapunov function, not necessarily, I mean. So we need to verify whether this proposal will be accepted by the learner. So we have a verifier which actually will act adversarially here. So it either tries to verify that the Lyapunov function is a valid Lyapunov function, or it will reject it with a counterexample, and it generates this counterexample in an adversarial way rather than randomly. So here we have an illustration of the overall procedure. So in the first figure, for example, we have 4 samples, so 4 affine constraints. The learner chooses this point, which is not in the target set F here. So basically what the verifier does is that in the next iteration, the verifier proposes this constraint and says, okay, I found a constraint that for which your point is infeasible. So this is in the spirit of cutting plane methods, right? So then the learner basically, based on this new constraint, proposes another point. And then this procedure continues until the learner can find a point inside the set, and the verifier certifies that. Here's a little bit of the details of the approach. So the learner basically finds a Lyapunov function based on finite samples. So the learner needs to basically solve a semi-definite program in order to find basically a valid Lyapunov function. And then it proposes a matrix P to the verifier. And the verifier tries to basically find a counterexample. So it tries to maximize the Lyapunov function difference and basically certify that if it is positive or negative. So if it is non-negative, this means that the Lyapunov function proposed by the learner is actually a valid Lyapunov function, and we can terminate. Otherwise, if P star, the global solution to the maximization problem, if it is positive, this means that X star, which is the global solution to this problem, is a counterexample. And this counterexample will be added to the sample set of the learner in order to refine the feasible set that it has in order to find a better Lyapunov function, right? And then in our results, we basically show that this algorithm is guaranteed to terminate in at most n cubed over epsilon squared iterations. So n is the number of parameters of the Lyapunov function, and epsilon is basically the radius of a full dimensional ball inside the original set, basically F. So if the original set F is basically full dimensional and is solid basically, then the number of iterations to find a Lyapunov function is bounded by that. One last thing is that how to solve this global optimization problem. So I didn't discuss that. So here we see that we need to solve a global optimization problem. It doesn't seem to be convex for general F. So basically we are claiming is that we can find a global solution to this for a variety of dynamical system for which we have either a mixed integer representation or complementary representation, basically. So the verifier needs to solve a non-convex problem of this form. We can write it down as a constraint problem where we have X and Y. So X is the current iterate of the dynamical system, Y is the next iterate. So this has to be in the graph of the function. And we argue here is that as long as we can find a tractable representation of the graph of the dynamical system, like in ReLU that I discussed before, we can basically find a tractable way to solve this problem globally. And there are various classes of dynamical systems, for instance, mixed logical dynamical systems or hybrid systems, for instance, which René has worked a lot on that before. Linear complementarity systems, for example, in mechanical systems with contact forces in robotics, bipedal robots, for instance, or ReLU neural networks. So if our dynamical system is parameterized by a ReLU network, basically we can find a Lyapunov function using this counterexample guided framework, and then we have done simulations in order to find Lyapunov functions, and then basically find Lyapunov, basically find regions of attractions or inner approximations of the regions of attractions. So I will pause here if there are any questions before I talk about the last part.
I was curious about the other optimization problem. Yes, the learner problem. So this is the one that is updating the Lyapunov function. And maybe I missed it, but how is the Lyapunov function parameterized and how does it get updated? And therefore, how hard is this learner problem?
Mm-hmm. So basically, the Lyapunov function that we have is quadratic. So it is x transpose px. P is a positive definite matrix. And then finding a, so basically, in order to, so there are infinitely many matrices P that satisfy the Lyapunov conditions for these samples. So we choose the analytic center of the feasible set that we have learned so far to do that. And the intuition behind is that the analytic center tries to find the deepest point inside the feasible set. So with the hope of finding a valid Lyapunov functions more and more quickly. And regarding the complexity, so the complexity of this is that basically, so the number of so as you can see, the complexity is just, we will have a summation here over the number of samples. So we will have more terms, but basically this is not a bottleneck compared to the dominant operations in a semi-definite program, which is inverting the Hessian matrix, for example, in the interior point method.
And so, sorry for the very naive question, but why is it the case that a solution is guaranteed to exist with the restriction to quadratic Lyapunov functions?
Excellent question. There's no guarantee. So basically, as if I go back here, this set F to begin with might be totally empty. And we have also worked on that, which I have not discussed that, which are basically, we have a different, actually we have also proposed a family of Lyapunov functions that are more complex in X, right? They are still linear in P. For instance, for example, you can think of Lyapunov functions of this form, where instead of having X, we use phi of X transpose PX, like the way that we do in kernel methods, right? And then we can parameterize phi by a neural network. We haven't done that. So what we have done is that.
That was exactly what I was thinking. And therefore the update would be an update of P as well as weights of the network. And in fact, maybe when phi is a neural network, you don't need the P maybe.
Exactly. The issue with that is that as soon as we lose linearity of the Lyapunov function with respect to the parameters, then we lose convexity of this set. So we heavily rely on the convexity of this set. So we try to be linear in the parameters of the Lyapunov function as if we can. Thank you for the great question. So I will answer questions at the end of the talk if there are any questions in the chat, but let me go over the last part of the talk. So which is about enforcing robust control guarantees within neural network policies. This is a joint work with my collaborators at Carnegie Mellon University. So basically, robust control is about designing controllers for models with bounded uncertainty. So if you have a dynamical system that you would like to design a control law for based on measurements and then propose some control law, in robust control, we typically have a model of the system, even uncertain models. And then in robust control, we design a controller that for the worst realization of uncertainties. So that's why we call it robust control, because it always considers the worst case realization as uncertainty, and there is no learning, and it always is a pessimistic approach to designing a controller. So because of this pessimism, we have deterministic guarantees that it always works, but it might have poor performance because it is very conservative, especially when we have a large uncertainty sets and there is no learning. So let me contrast this with deep RL. So in deep RL, we assume that the model is unknown, or at least we have access to some high fidelity simulator of the dynamical system. And our goal is to learn a control policy, either first by learning a model of the system, do some system identification, and then design a control policy, or directly interact with the unknown system and find a control policy. And in DeepRL, we parameterize the control policy with a neural network because of its expressive power. And the goal is to basically use data to learn a control policy. So one caveat with this approach is that there is no guarantee, or at least at most the guarantees are probabilistic, because we are not making any assumptions about the model. However, this approach, because it is directly interacting with the system, so it has the potential to achieve superior performance to robust controllers. So the basic question here is that, can we have a middle ground in between? Meaning that, can we use data, and if we have an uncertain description system, can we combine these two information in order to improve performance while enforcing the same guarantees, worst case guarantees, that we have in robust control? So that's the question that I'm going to discuss now in the last part of the talk. So our approach, to summarize, consists of 4 main steps. So we're going to work with uncertain dynamical systems as in robust control. So we have the uncertain dynamical system, which is composed of the known part of the dynamical system, which is typically a linear system, and then some uncertainty. And then we are going to assume that we have a family of uncertainty. So we have an uncertain description of this dynamical system. And then we are going to use a neural network to parameterize our control policy. And then, in order to basically enforce the guarantees that we are interested in, we are going to add a projection layer at the end of the neural network, which basically takes the output of the neural network and projects it back to some set that I will describe, in order to basically produce the final control action. So our approach consists of 4 steps. So let me describe the steps one by one. So first, we start with robust control design. So in robust control design, first we have a description of the system. So here we work in continuous time. So we have a state space representation of our uncertain system, where we denote Q as the input of the uncertainty and P as the output. And so for the rest of this part, I'm assuming that all we know about this uncertainty is that it is the L2 norm of this uncertainty is bounded by 1. Right? It could be anything, but as far as the L2 norm is bounded, then we are going to provide guarantees. Basically, and then we consider, so we would like to, the goal is to design a baseline linear controller along with the Lyapunov function as a stability certificate. So we are going to consider quadratic Lyapunov functions parameterized by matrix P. And then we are going to use linear control policy U equal to Kx. Our goal is to find this matrix P and gain matrix K for the linear controller to guarantee exponential convergence of the Lyapunov function to 0. So we are going to stabilize this system exponentially fast using a linear controller. So these are well-known results in robust control. So I just skim through them very quickly. Basically, we can, by reparameterizing this matrix P and K, which also Mariam talked about, if we define reparameterize K in this way by Y S inverse, where S is the inverse of matrix P, we can find a convex parameterization of this non-convex problem, right? So if this linear matrix inequality is feasible, where the decision variables are matrix S, Y, and this scalar mu, which is non-negative, then we are guaranteed to have exponential stability for all realizations of uncertainty. So basically, we have a robust result. So we have an infinite number of Lyapunov functions and controllers that satisfy this constraint. So we can go ahead and basically optimize some performance function as well. For instance, typical objective function is LQR, so we can also minimize the LQR cost function. So I skip the details because these are known robust control. Basically, we can find a convex optimization problem here in order to find the linear control policy as well as a Lyapunov function. So basically, more precisely, this is a robust LQR because we have uncertainties as well. So after finishing step 1, step 2 is to use the Lyapunov function that we had and then get rid of the linear controller. So we are not going to implement the linear controller. We're just going to use the Lyapunov function that we obtained from the linear control law and define the set of the so-called robust actions for the system. I'm not defining any specific control policy. So this set of robust actions is a set of inputs for which the Lyapunov function, which we have derived in the previous step, is guaranteed to decrease. And then basically this set is like convex for a variety of uncertainties that we have in robust control. Specifically for this uncertainty model that we have, we can basically characterize this set as a second order cone constraint, which is a convex constraint. So we can see that we have a set of constraints on the control action, which is also parameterized by a state X. So it's a state dependent set, right? So the set is convex and it also includes all the linear controllers in particular. So the set that we obtain is state dependent but convex, and the linear controller that we design is a part of that by construction. But we have a formal proof, of course, for that. In the third step is that, okay, after characterizing this set of robust actions, we are going to design a projection layer. The goal of the projection layer is that basically project the output of the neural network onto this set for any state that we have, right? So this is a real-time projection depending on what is the state of the dynamical system, right? So the big picture is that rather than restricting ourselves to a linear control policy, we are now allowing ourselves to take potentially nonlinear actions, but safe. So this is a safe set of actions, but they can be potentially nonlinear. And by doing this projection, we are going to guarantee safety, robustness, or whatever property that we are enforcing here. The property is Lyapunov stability. So in a nutshell, the resulting policy will have the same guarantees as a robust control policy, but it can learn a potentially better nonlinear controllers using RL methods. So now we can think of parameterizing our controllers using different techniques. Here we have used neural networks to parameterize our control policy. And the step 4, the last step, is mainly about how to basically make this a practical implementation of the method, because doing projection would be very difficult, especially if we have a state-dependent projection. Basically, what we do here is that after reformulating this projection problem and consider the dual, we basically solve this problem using projected gradient descent, where the projection can be simply done in closed form in the dual space. And we can also add nested of acceleration. So this allows us to basically solve this optimization problem and basically in batch, meaning that if we have multiple states, for example, when we are training a deep RL policy, we have a batch of samples. So we need to solve batches of optimization problems. So we can basically do this in batches. And I don't go over the details again. Basically, this optimization problem is a convex optimization problem. And if you write down the KKT condition, the KKT condition basically is an implicit equation that defines a relationship between X and U. And then using implicit function theorem and differentiating through the parameters of interest in that KKT condition, we are able to basically find the derivatives that we need to have in order to do chain rule and back propagation in a deep RL method. So in summary, we are going to basically implement a projection layer that can be integrated into deep RL like training methods and make it differentiable. So that we can do this during training and after training as well. Basically, that was the last part. And then basically we have also tested it, that we are showing that basically our method is, in the worst case, it works like as competitive as robust LQR, but on the average case, basically it is able to reduce the LQR objective compared to the robust LQR. So the margin is not significant, so we are able to obtain a slightly better performance out of this neural network policy, but there are a lot of room for improvement for that. For example, using better Lyapunov functions or learning Lyapunov functions as well, in order to further improve the performance of this framework. So basically that concludes the third part of the talk. So basically in this talk, I talked about different techniques in order to verify neural networks either after training or basically enforce some of the properties that we're interested in during training in neural network dynamical system. There are several challenges for this framework. We need to develop fast methods to verify industrial scale neural networks. More specifically, we need to develop a scalable semi-definite programming methods, and also other future directions would be how to integrate optimization constraints more efficiently during the learning process, how we can basically characterize these constraints that we are interested in and incorporate them during learning, and also learning-based control with large uncertainty sets. So how we can actually reduce conservatism when we have large uncertainty sets. And with that, I would like to conclude my talk, and thank you so much for listening. I would be happy to take questions.
Thank you, Mahyar, for a great talk. In fact, the first question from the audience is exactly your last comment. So I'll read it. Robust control often brings conservatism to the results. What do you comment on it? How do you suggest to reduce conservatism on your approach?
Basically, so for instance, we can adopt a similar approach that I talked about the second part of the talk, which is to first start with a very, very crude description of the uncertainty set and try to learn better uncertainties as we collect data. So we are going to reduce the uncertainty set. So we're going to shrink the uncertainty by collecting samples over time. I guess that would be one approach. The other approach that some people do but lead to probabilistic results is just basically, using concentration bounds in order to first find small uncertainties, do system identification, find these uncertainties with probabilistic guarantees, and then basically design a controller for those uncertainties.
Wonderful. Professor Theoretic raised his hand, but I don't have a question. So Yanis, if you want to type it in the Q&A, I can send it to Mahyar. Here it is. He writes, Hartman-Grobman within a Bayesian boundary maps a system to the linearization, and the transformation fails on the Bayesian boundary, where the Lyapunov function would go to infinity. It seems like a comment thus far. Maybe he didn't finish typing the question. I don't know if you have anything to say. Would it make sense to combine transformation to linear with finding a good Lyapunov function?
That's a very nice question. I don't have a answer for now, but yeah, I would be very curious to discuss that with Yanis offline too.
Yes.
Yeah.
Enrique, you had a question?
Yeah, I think it's sort of related. In your second part, you were discussing finding this Lyapunov function. So is there any part of that search algorithm that tries to increase the size of the Lyapunov functions, or in a sense, like trying to find a Lyapunov function that like gets most of the region of attraction?
Are you asking that if you're increasing the complexity of the Lyapunov function?
Well, mostly it's like, there's some ways to estimate the region of attraction where you basically try to increase the volume of the invariant set, things like that. Are you doing something like that, or are you just concerned of finding
So once we find, no, we don't have that basically in our learning verification approach. But at the end of the day, we find the Lyapunov function and find the largest sublevel zero, like not zero, but largest sublevel set of the Lyapunov function that will act as inner approximation of the regional attraction. But yeah, we don't explicitly have any objective function that penalizes small volumes, for example, but that would be an interesting to explore.
Yeah, nice work. You're muted, right?
All right, thank you very much, Mahyar. And maybe Han-Chen can connect. The rest of the session will be moderated by Professor Angie Liu. She's a new assistant professor in computer science working in robust machine learning. And she just became affiliated with Minds, I think a few weeks ago. So I apologize, I didn't have her on the slides earlier today, but welcome, Angie.
Thank you, Renee. Han-Chen, okay, I see the slides. Cool. It's my great pleasure to introduce one of our own. Han-Chen is a fourth-year PhD student in electrical and computer engineering at Johns Hopkins, advised by Professor Enrique Malada. His research interests include deep learning theory, reinforcement learning, and network dynamical systems. His work has been supported through the Minds Fellowship. Today, he's going to talk about the convergence and implicit bias of overparameterized